Hello everyone. For final applied deep learning project, Hima and I have decided to work on quantization of machine learning models. So the first question arises is what is quantization? So quantization is a process of basically reducing the precision of numbers used to represent the model parameters. So by doing this, what we tend to do is we reduce the scale of integers which are represented in float 32 into smaller bit integers. This can be helpful for like faster inference and without loss of any model performance. So here we have one example where the orange line represents the original scale and the blue line represents the quantized scale. So the numbers from the orange scale are represented in the blue line scale, which compresses the real values to a smaller scale, which helps in faster reducing the size of the model and faster inference. So why do we need to do this? So recent deep learning models like VGG have like millions of parameters in them. But the question is, do we really need them? And is it feasible to deploy them into smaller devices like microcontrollers and mobile phones? So these models take up a lot of space, and it's not feasible in real life to deploy a model of like 100 MBs just for the classification of images tasks. So the problems associated with these models are like they have like high storage capacity requirement, and with that it takes a lot of time for inference and training, and it also is costly due to its GPU requirement. So the need arises to quantization, which helps in reducing the storage size for those models. Uh, it takes up less memory, and inference can be done at a faster rate. So we explored three types of quantization in this project. One is post-training quantization, one is quantization await training, and pruning weights. So let's take a look at post-training quantization. So the idea here is we quantize the already trained model. So for example, here we can take, let's say a pre-trained resonate 50 and then quantize it, which would like reduce the storage capacity by almost 3 to 4 times, which can then be help to improve the inference time as well. So there are like two types of post-training quantization that can be done. One is full integer and one is float 16. So in full integer, we can further divide it into two parts where there's int8 model and int16 model. So in int8 model, all the operation weights and activations are converted into 8 bits, whereas in int16 model, we convert the activation to 16 bits and convert the weights into 8-bit model. So the model sizes for both int8 and int16 are almost similar to each other. Another thing is like while compressing the numbers from float 16 to int8 or int16 to optimize the model, it requires a representative data set. So that helps in accurate optimization. Another model, the float 16 model, is where we convert the weights into float 16 while the inference input and output are maintained at float 32. So these are mostly useful for GPUs, where GPUs are mostly optimized for float 16 models, and this helps in cutting down the model size by almost 2 times. So following is the formula usually used for converting the float 32 value into int8 or int16 scale. So what we did for this was we trained a simple CNN model on CFA10 and Fashion MNIST, and we achieved accuracy of like 70 and 89% respectively. And then we converted this trained model into int8, int16, and float 16 using KFLI converter. We then observed the accuracy of the model size, and inference time. So these are the results that we found out. So if you look at the CFA10, for the results for the CFA10, we see that the model size for float 32 is around 0.2 MB, and we can see that for float 16, it's almost 2 times less, and for int8 and int16, it's almost 4 times less, with very insignificant loss in accuracy. The inference time here was like 0.30 on collab, so it may not be representative for the intake models because of the overhead for converting from to float 32 and again processing those time. But for float 32 and float 16, we see that it's very fast as compared to int 8 and int 16. Similarly, the same fashion, like similar results are obtained for fashion MNIST, where we see like the model size decreases by 2 times from float 32 to float 16 and almost 4 times from float 32 to int 8. So let's take a look at the code. Uh, so here the first part we go through like creating datasets, loading the data from TensorFlow inbuilt dataset for CFAR10 and FashionMNIST. And then this function here helps us to visualize like sample images from the training and testing set with two labels. Then here we define the simple CNN architecture with 3 convolution layers and max pooling. Then we train this model and just observe the accuracy here, accuracy and the loss function on the validation set. We stop this training. Then we convert this original model into using the TF light converter. So this basically is converting the train model and we use this for like optimizing into we convert it into TF light model, and then which is then further quantized here, which is present in this code. So the first section here is for the input date where we provide the representative data set here, and then we convert all the supported operations by TensorFlow into from float32 into built-in integer, and then we convert the float32 model to to integer 8 model. Similarly, we convert the in16 to the float32 model into in16 by converting the float32 operations into integer 16 activations and converting the weights to integer 8, and again convert the model. Similar thing is done for the float16 model, and this code block is used to identify the input and output, like inference input and output data types. Next, we save the models into like bytes onto the disk, and then these are the just helper functions for predicting. So basically, we start with like initialize the interpreter here, get the input and output details, and then perform prediction on it one by one. So this is just a helper function to get the prediction from the TF light model. So this function is basically to again similar helper function which calls the above function TF light model by passing the save TF light model and the index image which we want to predict. So after running the above function, we can see the output like this, where we can see the input image, the true label and the predicted label for each of the models. So first model is float32 model, second is quantized integer 8 model, third one is quantized integer 16 model, and last one is quantized float 16 model. This evaluate model function is basically used for calculating the accuracy of this TF light model. So this basically calls the again prediction function which was written above for all the testing images, which are like 10,000 images. And here we just calculate the accuracy and like time for all the testing images for all the 4 different quantized models and the float32 model. Next, we measure the model size which was saved onto the disk, and here we can again see that this one is for FashionMNIST, where the float32 model is again 0.2 MBs, and then the float16 model is roughly half the size, and int8 and int16 model are roughly 3 to 4 times less as compared to float32. Finally, we measure the inference time over like 100 random images and average it over this 100 images, and that's how we calculate the inference time for different models. Next, I will pass on to Hima to talk about quantization aware training and float weight pruning.
Yeah. Okay. So next we worked on 2 more types of quantizations. First was quantization aware training and the second was pruning. So let's talk about quantization aware training first. So in QAT, we basically try to create a model that can produce an actually quantized model. So during training, the model tries to understand where can we introduce losses caused by training without compromising a lot on accuracy. So different types of quantizations here can be done, we can go lower in the precisions. So from float 32 or float 16, we can go down to int 16, int 8, and even int 4. But int 4 really reduces the accuracy a lot. We can quantize both activations, weights together or separately, and we can also specifically custom quantize layers or the whole model. So methodology is similar to the principle of quantization. When we have a float 32 memory space, we don't really need it. The whole distribution of the weights does not require the whole space. So we can choose a min and max depending on the weights that the model creates, and just bucketize our information in these in this smaller range, therefore saving a lot of space. So there are two steps to QAT. First is first creating a model that is quantize aware, and then using this quantize aware model to create an actually quantized model. So this is basically the methodology of QAT. So we ran this process using fashion MNIST dataset over different precisions, specifically towards quantizing only weights and not just activation. So the first 4 rows in this table are the results for just weight quantizations. I'll talk about the last result soon. So we see that in general, as the precisions decrease, that is, we go from float 16, which is default, to int 16, int 8, and int 4. In general, the trend is that the accuracy decreases, and the model size also decreases more or less, and the inference time also is lesser. It's important to check inference time and not training time, because here the process is of creating a quantized aware model while fitting and not the quantized model. So the real difference comes during inference time. Coming to the last row in this results table, that was an experiment which included quantizing the weights as well as the activations, and that is actually the actual API created by TensorFlow and gives comparable accuracy as a float 16 model would do. So we see that the accuracy is really good, and the model size is 1/4 of the actual model size. Inference time is also very low. I can quickly show the code for this. So this is the 16-bit quantization aware training process. So first we create a model without quantization aware training. So we have our normal CNN model with some convolution layers, max pooling, etc. After defining this base model, we can convert it using this class. So this class converts dense layers activations to lower precision activations. Using that, we create a quantize aware model, and after compiling and fitting, we can check its accuracy, inference time, and also after saving it to disk, we can check its file size, which is reduced. Similar process was done over 8 bits, 8 bits with unsigned activations. That was the last row, and then we've also done it for 4 bits. So these were all the experiments with quantization aware training, and we did realize that it is very much possible to reduce the precision of activations and still be able to get accuracy as is shown in the last experiment done by us. Next quantization method we chose was pruning. So pruning is basically a process where we zero out model weights during the training process, and we achieve model sparsity. So we have lesser weights than we would normally have. And these sparse models are easier to compress, and during inference, these zeros can just be skipped. So we get faster inference for a pruned model. Methodology is as simple as that. We just set the individual weights in the weight matrix to 0, and the weights which are least relevant are first picked and set to 0 during training time. So from our experiments, we understood that we don't really need most of the weights that we usually get after a trained model. So from our process, we understood that if we remove even up to 80% of the weights, we still get the same accuracy. We did this on two models. First was a simple custom model, similar to what I'd shown before, and one was a deeper model. So we can see if we plot the accuracy, which is on the y-axis, with the sparsity, which is on the x-axis, the sparsity is ranging from 0%, and then it starts with 50 with a gap of 10 each. So 50, 60, 70, 80, 90, and 99. These were the sparsity levels that we had experimented on. And we see that up to a good 80%, we don't really need a lot of the weights. So we can get rid of those weights and still have comparable accuracy as our fully dense weighted model would have. Coming to the code walkthrough for this. So first, as before, we create a model without pruning and we check its accuracy. After that, we start the pruning process. So I can take an example of 50% pruning. So there is an initial sparsity level set which starts with from 0 and a final sparsity level which is 50%. So during training in each epoch, the least relevant weights are removed uh, till the sparsity level reached is 50%. So I've defined similar models for sparsity, different sparsity levels, 50, 60, 70, 80, 90, and 99. And I have fitted those models as well. And after fitting, I have plotted out the accuracy change that we see over different sparsity levels. And this is also done on a deeper model, and we get similar results, although here it drops a little sooner. In the first custom model, it drops only at 99% sparsity, but in a deeper model, it drops at 90s. But the trend remains the same, that we don't really need most of the weights for getting the same accuracy. Yeah, so that is sparsity, and we specifically did weights pruning and not neurons pruning. In neurons pruning, the whole neuron is set to 0 and it is not taken into consideration while inference or training. We worked on weights pruning specifically. These were the references we used. So we used the official TensorFlow guides and the paper that introduced the idea of quantization. Yeah, so thank you so much for listening.